So it's my pleasure to introduce our today's speaker, Marcin Moszyński, professor from Warsaw, and who you're also a long-term visitor at earlier institute. So please.
Thank you. Unfortunately, I forgot the full name of my talk, but it will be about subordination theory for scalar Jacobi matrices and some possible extensions or generalizations for block Jacobi matrices. Yes. So I tried to prepare this short, but we shall see. Probably it's not so easy to make such talk very short. So let me start from some basic things which we need to formulate the theory for scalar case. But to omit some repeating similar things for block case, so I will define the main object, so the operator, Jacobi operator, maximal Jacobi operator for general case. As block case, we can think about the scalar case as a block one-dimensional case, so it will be okay. So this is the first step. We assume that this is the dimension of blocks, is 1 or bigger. So we consider block D by D Jacobi matrix first. So in some sense this is just the formal object. So the matrix would be like this. This is half infinite. In the plus infinity directions. So, and here are blocks. So this is three-diagonal block matrix. So on the diagonal we have matrices B0, B1, B2, and so on. And upper and lower diagonals are defined by A0, A1, A2, and so on. And here the same but adjoint. A0 adjoint, A1 adjoint, A2 adjoint, and so on. And here zeros. So this is the formal object, and now I will define also something we call formal, but this is a more concrete object. So the formal operator. So first let us denote by LD. LD, this is just the space, not Banach or Hilbert space, but just the space of all sequences of all sequences from N0. So sequences means functions, yes, from N0 to CD. Yes. So on each term, for sequence like this, on each term you have a vector from CD. In particular, when D is 1, we have just a sequence of complex numbers. So this is LD, and our space, the important space, will be denoted by L D2, yes, and it's the typical Hilbert space. You can write it like this. This is the space of all x equal to xn, where n is like this, belonging to D, such that the sum of the norms in CD x n from n0 to infinity is finite. So this is the space with the natural inner product, scalar product, yes? And this is the formal space, we can say. So using this...
Square. Square.
Of course, square. Yes. And of course, when we take the square root of this, on this we obtain the norm. Yes. Yes, of course. So this is L2, and when D is equal to 1, I just omit this. And L2, okay, without those 1. So this is a notation. And first, we define just the formal operator. Which is given by this matrix. Yes, this is the formal Jacobi operator. I will use calligraphic letter for it. This is something which is an operator from LD to LD, the inner operator given by this matrix. So we can write down it's J of X is a sequence which for n has a value, and we should compute it. So this is A n minus 1 adjoint x n minus 1 plus b n. I forgot, of course, it's important to assume here, we assume, of course, that B are self-adjoint for any j, for any n, and A are invertible, are non-zero, determinants are non-zero. This is important here. And here we have xn plus a n xn plus 1, but here, of course, what does it mean? A minus 1, it's not important what we can take it just to be 1, for instance, and x minus 1 equal to 0. That's because here we have only this, yes, without a, yes. So to make sense, this for n equal 0. Okay. So this is the definition of the formal operator, but it's not an important object, but it's convenient to use this to define something what is important for us. So Jacobi operator. Our Jacobi operator will be the maximal. We consider the maximal operator. It's important because generally we use the name Jacobi operator for some extensions of such an operator restricted to finite sequences. For each, usually for each extension, we use the name Jacobi operator or block Jacobi operator. And here we will just this theory, the subordination theory, is about maximal operator. Yes, and this assumption is sometimes important. So I will call it here Jacobi operator. And this is with capital J, not calligraphic like here. Capital. So what is this? This is just this formal operator is restricted to the domain, so-called maximal domain. And this maximal domain is like this. We take all the sequences from LD2 such that the formal operator moves this into A2. This is a maximal domain, and then we have a linear operator in L. We consider this as an operator in L2D. So this is a symmetric operator. Oh no, sorry. On such domain it can be symmetric or not. Just symmetricity in this case it is the same with self-adjointness, but on the smaller domain, when we restrict this to the smaller domain, which is the smallest in some sense interesting domain of finite sequences. So on finite sequences it is symmetric, of course, because of the assumptions here that on the diagonal we have self-adjoint operators. Yes, but we will assume generally that for our theory it's important that we consider self-adjoint case. Yes, and there are many, there is a theory when it is self-adjoint or when it's not self-adjoint, but this is the subordination theory is for self-adjoint case. Okay. Now I will define the notion of generalized eigenvector. So what is this generalized eigenvector? For z in complex Z and J, formal J, you say. So we denote by G, E, V of Z. This is a space or set. This is a space, two-dimensional space, but not a subspace of L2, but the subspace of LD just. This is a space of sequences, which are, we can say, almost the solutions of the eigen equation for J. Formal J and Z, but except the first term. Yes, so we should define this like this. This is the set of all such X in LD that J X. This is the formal operator J X. The term number n is equal to zxn for n, but except 0. We do not assume this for 0. This is important. Yes. And observe. What does it mean? It means that for all n starting from 1, we have the recurrence solution, recurrence equation of the form something like this is equal to z times xn. Yes? So, starting from any x0 and x1, we can use this recurrence, and because what does it mean? It means that we can compute using the invertibility of ANs, we can compute xn plus 1 by a linear manner from xn and xn minus 1, yes? So it's easy to see that in the case when d is equal to 1, then this is just the space of sequences of the dimension 2, because we have a freedom of choice of 2 of the values of on the term number 0 and term number 1. And when the dimension is d, we just have the dimension of this space equal to 2d, 2 times d. Dimension of d, this is a linear space, of course, the dimension is equal to 2 times d. Okay, so this is the space of generalized eigenvectors. And now, and what you should remember that this is in LD, not in L2D. If we restrict ourselves to such a space, it's less than this, yes, usually. Okay, then something which is more specific, formal eigenvectors. Formal eigenvectors are such generalized eigenvectors which satisfy also the condition for n equal to, but still are not necessary in this space. Yes? So I will write generalized eigenvectors plus the condition Jx for 0 is equal to zx0. Yes? Which means that this is equivalent to say that just x is formal eigenvector if and only if this is an eigenvector of the formal operator. Yes, this is a linear operator, so it makes sense for z. So this is we can say this that j formal on x is equal to zx, just this. Yes. Okay. Okay, I will call this condition, I will call star condition, okay? I will denote this by star for 0, this condition for 0. Okay, and now simple fact. X is okay. Maybe let me write it like this. Now we take our operator. This is capital J. Jx is equal to lambda times x. Lambda is also a complex number. In fact, it should be a real number when J is self-adjoint, or x should be 0. So this condition is equivalent to the following conditions, where x is generalized eigenvector for lambda, and the condition star holds for lambda and x belongs to to D. Of course, why this is true? Of course, this is obvious, yes, because this is an operator in L2, so the x should be in L2, and it should satisfy also the formal condition, yes, for the formal operator. But why this direction is also true? So it is the place when our choice of the domain is important, that this is a maximal operator. So observe that what does it mean that this is hot? Of course, it should be not only an element of L2, but we should be sure that x belongs to the domain. And then, when it belongs to the domain, we have right to write the eigenequation, yes, on this. So, assume that this is satisfied, and first, what can we do? These two conditions means that for the formal operator, we have Jx is equal to lambda x. And moreover, we know that x belongs to L2. Yes? So this also belongs to L2. So this belongs to L2. So together we get the condition, this and this means that x belongs to the domain. Yes? So this is true also. Because this is just the restriction of this to the domain. Yes? So this is the place, it's obvious in some sense, but this is the place when it's important that we consider the maximal operator. Not only one, but in some places it's important. Okay. Now we, for a long time, we assumed that D is 1. Okay? So we consider the scalar case. We have just the scalar Jacobi operator, and we will consider the self-adjoint case. I can recall that when we want to consider another typical Jacobi operator, so-called minimal Jacobi operator, which is the closure of the Jacobi operator considered on the finite sequences, then the self-adjointness of those two operators is the same, just the same, and when we assume the self-adjointness, the minimal and the maximal are also the same operator. So this is not very big restriction, but we should remember that this theory does not obey the case of such situation when there exists a lot of self-adjoint extensions of the minimal operators, and sometimes we call them also Jacobi operators. So for such kind of Jacobi operators, this theorem is not valid just. Okay. So I will soon define subordination solutions, but first I would like to study some generalized eigenvectors in L2. So what is almost obvious? You can say this is fact. If J is self-adjoint, then the dimension of the intersection of the space of generalized eigenvectors for Z, then for any Z which is non-real, yes, the dimension of this intersection of this with the L2 space, so you can say the space of all L2 generalized eigenvectors is just one-dimensional. And it's easy to prove because, first of all, it cannot be the maximal dimension is 2, because this is two-dimensional. But it cannot be two-dimensional because if we when we have two-dimensional, it means that each generalized eigenvector is in L2, yes? But then we can just choose such initial conditions which satisfy this star condition, which means, using the fact here, that we obtain for such a z, at such a z, we obtain a non-trivial eigenvector, which means that this belongs to the point spectrum, which is impossible because this is self-adjoint operator. So it cannot be two-dimensional. So it can be zero-dimensional or one-dimensional. And we can easily find a vector which is non-zero and belongs to this. How to find it? We should just use the resolvent. So take J minus Z identity to the power minus 1. So this is a resolvent operator. It exists because operator was self-adjoint. And let us apply it to the first, or we should say zero base vector standard from the standard base in this space, yes? So A0. So what is A0? A0 is just the sequence which on the zero stem has 1 and then zeros. Yes, this is A0. So let us take this and call this X of Z, okay? So this is a bounded operator in our space, so it belongs to L2 space, of course. And what we can get about this operator? So we can just apply J minus Z identity to both sides, and we see that J minus Z identity on the vector X of Z from L2 is equal to A0, yes? So let us check the terms, all the terms of both sides. So we take the number n for n greater equal 1. So for n greater equal 1 we obtain 0 here. And this means this condition, and this is equal 0 for all n greater equal 1. It just means that that it belongs to that x of z belongs to general eigenvalues and vectors of for z. Yes, and it is in A2. So and this is not 0, of course. It cannot be 0 because if it is 0, we will obtain 0 here, and this is not 0 because no, it's obvious. Yes, we cannot obtain 0 vector. This is not 0 vector. Yes, so this is a non-zero vector. Without this, we see this. Yes, it means that it cannot be 0. Okay, so the dimension is 1. And moreover, we know not only this, but we know more. We know that, moreover, we can write, moreover, this space is the linear span of one vector, of this vector, x of z, which is defined like this. I will try to leave this definition, but I hope maybe I should find a colored chalk. Okay. So now let me define subordinated solutions. Okay, so fix lambda a complex number. Usually we use the name subordination solution for the solution from a generalized eigenvector, which is for real numbers. But generally speaking, we can also consider complex. Okay. And consider x, which is a solution, generalized eigensolution, generalized eigenvector for lambda. Yes, and definition is as follows. And this is important that this is non-zero. Okay? This is a non-zero vector which solves our equation. X is subordinated. Subordinated solution for lambda. We should add sometimes if and only if for any other solution y which is a generalized eigenvector for lambda, and y is not linearly dependent on x, so does not belong to the linear span of x. So for n such y, when we compute something like this, I will explain it. So I take something which I denote by the norm n. In fact, this is not a norm, this is a semi-norm for each number n, natural number n. Here I take x, and here I take y. I divide this, and the limit should be 0. And what is this semi-norm? This semi-norm, this is just the partial sum of the L2 norm. But remember that we consider some sequences which are not necessary in L2. So L2 norms can be infinite, say, but such norms for n exist. So these partial sums and of course the square root, but this is not important here for the condition here. So for n u, a sequence u is just in the space L, a sequence, yes? This is equal to the sum, or let me write this for the square of this, the sum from 0 to n norm, this is the absolute value here, u n square. Yes, this is something like this. So, subordinated solution, of course, why this is like this? Well, if we take something which is a constant times x, we will not of course obtain 0, yes? But we will obtain this constant, yes? So this is why we take something like this. So we can say that the subordinated solution, if it exists, I don't claim that it exists for any lambda, but if we have such a solution, it means that this is in some sense, in the sense of such specific norms, it's the smallest solution which can be found in all those, in this space, yes? In some sense it's small because the limit is 0. Okay, so this is the definition. And of course, when we have a solution and we multiply subordination solution, multiply this by the constant, it's also subordinated. So this is the smallest up to linear independence, or up to linear dependence, maybe we should say. Yes. Okay, and some properties of such solutions, subordinated solutions. It would point 4, and now point 4 prime. Some properties. So property A is such a property that in this definition, instead of any, we can put there exists. Okay, into the definition. And point B is as follows. When J is self-adjoint, then if X is in L2, and this is of course generalized eigenvector for lambda, non-zero, then X is a subordinated solution. Why it's true? Oh, it's true because we know that there exists up to the linear dependence. There exists in the self-adjoint case. There exists maximally one. Okay. Maybe. We know this maximally one, we know this for non-real, but it's true also for the real case, that we cannot have two independent generalized eigensolutions in L2. It's more difficult to prove, but it's also true for real. And
can I ask you, can you describe the spectrum of the Jacobi matrix in case D is equal to 1? Is it discrete?
It depends. It can be any set.
Okay.
It can be, this is very general Jacobi matrix. When we do not assume something very special about those coefficients, okay. It's just, we can say, it's just, what is true? It's something similar to the Jordan block for the finite matrices. So it's like this, that each self-adjoint operator is a direct sum or prime sum of can be its unitary equivalent to the sum, of course infinite usually, sum, simple sum, yes, of the operators which are Jacobi operators or finite Jacobi operators. So finite matrices which are like Jacobi operators, yes. So we can say this, that this is a very general form of the...
Of course there is very general, but maybe there exists some special form when this operator, the operator of this form, has a distance vector.
Of course, yes, but I thought you asked about the general case. Yes, of course, such operator can be pure discrete, and it's very often has...
And then I don't understand this statement. Let us assume this case, and we consider x and y the eigenvectors that correspond...
No, these are not eigenvectors. These are not eigenvectors of the operator. These are only generalized eigenvectors. So these are the solutions I would like. Yes, this is two-dimensional space, but we do not. These are not. This is again generalized eigenvectors. They are generalized. These are not eigenvectors. These are only sequences which usually are not in the space. They are just sequences. They do not usually belong to the Hilbert space. These are just sequences which satisfies the equation and not everywhere except the number 0. We assume this only for terms n greater or equal to, and not for 0. So this is something when you consider the differential operator, you sometimes say that here this is a difference operator, but this is an analog of the differential case. You can say about the operator, which is a concrete domain and in the space, and you can say or speak about the equation, which is something more general. So we consider here only the equation, and this is the equation which can be satisfied also by some functions, here these are sequences, which do not belong to our space, yes? And moreover, we do not assume any concrete how to say, border initial values, yes? This is an equation without initial values, yes?
But if you take a special initial value, then you can obtain eigenvector.
I can, but it's not. But this is not enough to take initial values. But we also should obtain a vector from the space which belongs to the L2 space. Here, in the definition of this, I consider just X which are sequences, but they cannot belong to the L2 space. They can be very big for very large, for large numbers of...
You say that each element of this space does not belong to L2.
It can be, sometimes belongs, but I consider all of them. So this is why, so the notion of subordination...
Well, not then for any one, you could not obtain this convergence, because if you take only one, which is eigenvalue, and okay, there is exceptional, but nevertheless it belongs to this space. But this convergence will be wrong.
This is what I wanted to say. I wanted to say that when I take such a generalized eigenvector which belongs to A2, then it is subordinated in the self-adjoint case. Because when we take another one, which is not the constant times this one, it does not belong to L2 space. It cannot belong to L2 space. So this tends to plus infinity, just because the norm is the L2 norm is infinite, and this is finite. This is bounded by L2 norm. So this tends to 0. Yes. So automatically. So why it's important for us? This is important because we can say that subordinated solution is something which can be not in L2, but it's somewhat near to an element, a solution from L2. If it is a solution from L2, it's a lot, in some sense, because when we add the condition star, we obtain just the eigenvector. And here, it's something between the general solution, which is not very important, and a solution which belongs to L2. it's good to think about the subordinated solutions like something which is near to a two solution. Yes? Okay, so this is just the definition and the property. So I would like to formulate the theorem, but first I should define some notions. Yes, some more notions, but quite simple, I think. Okay. So about the restrictions of the measure now, the notation just. So suppose that we have a measure. Usually we will here consider the Borel measure on real line, but it's general. So we have a measure, the sigma algebra and the set, and S is a subset, a measure subset, so it belongs to the sigma algebra. And now the notation just. What is this mu restricted to S? This is also a measure on M. This is a measure on M. Generally speaking, like this. And this is just defined like this, that we take the intersection of omega and S. So we consider the measure not on S, but on omega and on this sigma algebra, but we cut it only to S. Yes. So this is just here is S. This is just the measure of omega intersected with S, and it's well-known fact that this is also a measure. Yes. So this is a restriction. Now, what is the support? There exists a notion of a topological support of a measure which is on a topological, on a sigma algebra which is generated by a topology, yes. But this is another notion. This is just strictly measure theory notion. So S is a support, because this is not a unique notion, a support of the measure mu, if and only if mu is equal to mu restricted to S. So this is a support. And now, when we have another measure here, we can define something which is called a minimal support. Is a minimal. It's also not unique usually. Minimal support of mu with respect to a measure, another one, like this for instance, on the same sigma algebra. What does it mean? It means just that if we take a smaller, if and only if, for any S prime which belongs to the sigma algebra and is smaller than S, if S prime is a support of mu, then the measure of the difference is 0. This extra measure of S minus S prime is 0. So in this sense, this is minimum. Yes, this is S, this is S prime, and it cannot be large. Yes, so of course, usually it's not also the unique notion, but it's a convenient condition sometimes. And in the case when we consider Borel real line and Borel sigma algebra, and this extra measure is the Lebesgue measure, we will just say that this is a minimal support without this, okay? For short. Minimal means minimal with respect to the Lebesgue measure, okay? Yes. And now I would like only recall that when we assume that our Jacobi matrix is self-adjoint, then we have a spectral measure for it, which is projection valued spectral measure. So if J is self-adjoint, this is the projection valued spectral measure. Projection valued spectral measure. So what does it mean? Well, in particular, Aj is from Borel sets on R into the projections, generally speaking, bounded operators in our space L2. Yes? And we also know that Jacobi operator, this is a capital J, of course, Jacobi operator always is a cyclic operator. So, and the main, we can say, cyclic vector is just A0. A0 cyclic vector for J. So this is a convenient situation when we have self-adjoint cyclic operator, and then we can say that the spectral information is contained in something which is also called spectral measure, but this is not the projection value spectral measure, but this is just the scalar spectral measure. And the scalar spectral measure for self-adjoint Jacobi operator, this is scalar spectral measure. This is the measure mu, which is just this spectral measure Aj for this cyclic vector A0. This is just the definition. We call this measure, we call the scalar spectral measure. Let me explain again this notion. What does it mean? It means that we have what is mu of omega, when omega is a Borel set. By the definition, what we should take? We take Aj, the projection Aj of omega, and then we apply this on A0 two times. A0. Of course, because this is self-adjoint projection, so we can also write that this is just the square of the norm of Aj omega on A0, yes, because we can write the square and put it one of them here. Yes, so this is the square of the norm of this. And this is a measure. This is a scalar measure which contains the full information about the operator, spectral information about the operator. From my mini course, you can know also that this operator is equivalent to the multiplication by x operator in the space just L2 on this for this measure. Yes. Okay. So this is very important object. So this object contains all the information about the operator, spectral information, and for instance, when we want to know something about the absolutely continuous part of this operator or the singular continuous part of this operator, it's enough to know the appropriate parts of this scalar measure. It's enough to know the absolutely continuous part of this measure in the sense of Radon-Nikodym, not Radon-Nikodym, I don't know, maybe this is not the good, okay, you know that each measure could be divided, is the sum of the absolutely continuous and singular continuous part, yes, so we can take those two parts and we can say that the absolutely continuous part is responsible for the absolutely continuous part of the operator and singular continuous for the singular continuous part of operator. And I will denote this part A absolutely continuous, AC, and A singular continuous. Yes, and these are two parts which are singular one to the other. Yes. Okay. So now I think we can formulate our main theorem. This is the theorem about
10 minutes.
10 minutes?
10 minutes.
Okay. So I will formulate the theorem and I think I will not say anything about the proof. And about the block case. But what to do? It is not so easy to describe this in 1 hour. Okay. This is Khan and Pearson theorem, which is just, we can say, the discrete case of Gilbert and Pearson theorem for the differential analog of this, which was proved before. So let J be self-adjoint operator and consider two sets, two subsets of real line. One is SAC, I call this SAC because it's connected with absolutely continuous spectrum. And this is the set of such lambdas real that no subordinated solutions for lambda exists. There is no subordinated solutions. This is one set. And the second is S singular continuous. This is a set of such lambdas that there exist such subordinated solution X for lambda that satisfies the condition star. So this was the condition which makes the solution a formal solution. So it is, we can say, almost the eigenvector for lambda, but almost, because we don't know that it belongs to the space. But it's almost belongs because it's subordinated. And now, what is the assertion? Then, first part is that this space SAC is a minimal support for mu AC, for this spectral measure, for the absolutely continuous part of this spectral measure. This is part 1, and part 2 is that sigma, that S singular continuous SC is a support, not minimal here, a support, in some sense also minimal, but it's a support for mu singular continuous, and the Lebesgue measure of this set is 0. So this is the whole theorem, and having this theorem we can prove many results in the special cases about, for instance, the absolutely continuous of some Jacobi operators and so on and so on. So, but this is just the theorem, the abstract theorem. Very it's interesting theorem because there is only one assumption, that this is self-adjoint, which is of course necessary to formulate something like this. So there is no other assumption, so it's very general. So it's very, very good theorem, and we can say that it gives a description of very important spectral properties of the operator in terms of only some solutions. Yes, we can say that we use just the difference equation theory. Equations. There is nothing about operators in this subordinated solutions. Yes, this is just something about the, we can say, asymptotic properties of solutions. So knowing a lot about asymptotic properties of all the solutions, we can obtain an important information, spectral information about the operator. Yes, so it's quite a good theorem. So if I have still 4 minutes, I will just...
6 minutes.
6, okay, so I will just draw a schema of the proof. Draw, yes, for this theorem. Okay, so we have 4 objects, we can say. The object A, this is subordination property of a solution, or non-existence of subordinated solution, or non-existence. The second one, B, is the so-called Weil coefficient function, a coefficient function on the upper half complex plane, and its boundary limits on the real line. The next one is the Cauchy transform of the measure, the spectral measure mu. And the last object, D, is, you can say, is the support of supports of mu absolutely continuous and mu singular continuous. And of course, in the proof, we have some links in both sides. To obtain such a theorem, we should both sides links. So, what kind of links? Okay, first, I don't know. Do everybody knows what is this? Maybe I will define it. The Cauchy transform of the The Cauchy transform of the measure is like this. We have a finite measure, yes. Cauchy transform of finite measure mu. So I take z belonging to P plus, the upper half plane, and the Cauchy transform of the measure mu at the point z is just the integral over R. Yes, this is a measure on R, and I take 1 over t minus z d mu of t. Yes, this is bounded function. This is a finite measure, so this is it's well defined. So this is a transform. Okay. Now, what is this? The Weil coefficient. Weil coefficient is something which is related to this. It's also defined for z, for instance, like this. Yes, and this is a vector. This is a vector in R2. This vector belongs to the space which is two-dimensional of generalized eigenvectors. So we can choose a base of this space, which should be, the base has two elements. And the typical base, which was not used in the original proof, but it's more convenient to take the base which consists of two solutions, Q of z and P of z. P of z is related to orthogonal polynomials, and this is also in some sense related to this, but what is this? To define this, we should just precise what are the initial conditions. And it's more convenient to use so-called conditions not in 0 and 1, but in -1 and 0. What does it mean, the condition in -1, when -1 does not exist in some sense? It's not so difficult to see, because we defined something like A -1. It was identity. So we can in some sense write the equation for the value in, it makes sense. So here we take, in -1 we take 1, and in 0 we take 0. And here we take the opposite, 0 in -1 and 1 in 0. Yes? And in fact, it is a formal eigensolution, and this is not a formal eigensolution. So these two solutions form a base of our space, and it means that this should have the form. It can be easily checked. It should have the form like this. It should be equal to Q of z with the constant 1 plus a number m of z, we call this m of z, times this. Why it is like this? It can be easily checked that we can there can be a coefficient equal to 1 just. And knowing this, and this is just the Weil coefficient function I wrote about. Yes. So this is this function. For each z, this is a number which is the value of the Weil function. And now you can easily prove that this is just the same. This and this is the same with such a definition. For the original proof of Gilbert and Pearson, it was not like this, because they chose another base. But there was also a formula, not very complicated. Okay, and now this is very important thing. There is a link between this and this. How? Knowing something about the existence or non-existence of subordinated solutions, how to obtain an information about the boundary limits of this coefficient. So we can say that they invented a method how to make the relation between this and this, and the main tool in this to obtain such a link is the variation of constant formula for some difference equations, and this formula has a very convenient and simple form for this situation. So this is something based on this variation of constant formula. Very delicate but quite nice, I can say, and this is very good. And then here, so here we have an equality, here I told you about, and here there is just abstract theorem. There is just an abstract theorem which says that the Cauchy transform has the limits or has not, and it depends of just this. it's related to some support of this. So this is a classic theorem which just we need to apply. And so using all those three links, we can obtain this theorem. And now in the block case, there I can say only this, that we still do not know what is the good analog of this notion. But we have something like this. We also have in this situation a good formula for and good variation of constant formula. This is very good, and we have an analog of this, yes, but we should say that this analog is based not on such solutions like here, because in block case it's more convenient and to consider matrix solutions. I have no time to say what are the matrix solutions, but it would be not the vector solutions but matrix solutions. Yes, and also those solutions would be quite well-known matrix solutions. And there exists also the theorem like this. And what is the measure? What is the measure? Instead of the scalar measure for the operator, we should use the measure I told about it on my mini course. The matrix measure, yes. We should use the matrix measure for the self-adjoint operator, which is finitely cyclic. And block Jacobi matrix is finitely cyclic. So, and we have also a theorem, an abstract theorem, which gives similar results. So, there are some questions, but it seems that something can be done with this also in block case. Thank you very much.
Thank you. These questions, comments? Maybe people who are attending lecture online also have questions or comments. I have a question for your operator. Do you have some particular class of matrices A0 and B0 for which you can describe the domain of the self-adjoint operator in A2 in more explicit form?
The domain?
I mean, I exclude, of course, the trivial case when the operator is bounded.
Yes, then
in unbounded case when there is some growth.
You know,
are there natural cases when you can describe the domain in a more or less explicit form?
I do not remember such a situation, because we can sometimes, using the subordination theory, even describe quite good the spectrum, and we can answer the question, is it, for instance, discrete or is it absolutely continuous? But unfortunately, I think that we usually even do not need any information what is the domain. I do not, so I don't know. I just don't know.
I see. Even if you don't need it, it's...
yes, maybe it's natural question, but...
sometimes it can give you some intuition about what's going on if you have more explicit.
Of course, maybe we sometimes know that some kind of subspaces are included in the domain. It's sometimes important, but to have just the formula, I think it's not so easy. I don't know. I really do not know anything about this.
I see. Yes, yes.
In the scalar case, you always have one subordinate solution.
No, I can have one, but I can have none. Yes, of course. So this theorem is about it. When I, for instance, when I have, when I am just say out of the resolvent set on real line, I have solution. I didn't write this, but it's also true that we can consider the difference between the whole real line and those two sets. So I obtain the set of such lambdas where there exists a solution, subordinated solution, which do not satisfy this condition. And it can be large set, but the spectral measure of this is 0. Yes. No, it's easy to see from this, from the assertion of the theorem. Yes, but I can have when the operator is absolutely continuous, I have on large sets I have no subordinated solutions.
Yes. But the question is how to generalize it. In the block matrix case, the notion of subordinate solution.
Yes.
Will there be one solution, or will there can be several such solutions?
No, this is a question, general question. In which kind of language should we, what kind of solutions should we consider? For instance, maybe it's better also for subordinate solutions, consider not the analogues of those solutions like here, but analogues of these solutions are just the vector solutions, yes? No, but maybe it's better to consider matrix solutions.
Is it possible to expect that there can be matrix subordinated solution? Subordinated.
Okay, what does it mean subordinated? We can make the formal definition similar to this. Yes, we can of course make this, but probably this is not the right way. Probably not. It's more delicate. So I should say that this is a subject I study with Grzegorz Świderski, and we are just thinking what to do, because many bricks, we have together, but there are some holes, and the main hole is how to define subordinacy.
So you don't have the answer?
We don't have an answer still. We answered many questions, but not this one. It's maybe strange, but it's interesting. It's a good question and not so easy. But okay, I am not so sure that we will obtain something very analog. But I would like only to get something in this direction. For instance, a theorem which could help us to describe, for instance, some parts of absolutely continuous spectrum for some block Jacobi matrices. It will be also very, very good. Because now there are of course some tools to obtain, for instance, Moore method, yes, to obtain absolute continuity. But these are very classical methods and very, I don't know, I don't like it. For instance.
Other questions, comments? If not, let us thank the speaker again.
Thank you very much.